afternoon to all. Today we are going to start the third module. So module 3, the time domain analysis. Under that we are going to see standard test signals, time response, time response of first order system, time response of second order system, steady state errors and error constants, types of control systems. So this much portions we are going to study today, and this is not as easy as what we studied before. This is little difficult. So all of you, what I need to say that little concentration is required. So little mathematical ability is required here, and the Laplace transform you should know. That is the thing, basis requirement of module 3. Today we will try to complete the time domain analysis. Apart from that, in module 2 some of the problems are remaining. That I want to say that you need to complete that by yourself. That if time permits, I'll try to do that. And the important thing I found that the second video I sent in previous class, only 16 out of 29 is watched. What about the remaining 13 students? It is I'll see that who all are not watched this. So for them I will deduct your attendance. So be careful here afterwards. What are the portions I'm telling that you should complete it within the time. Actively you should participate it. At the end of the class, I will ask questions. You have to answer me through WhatsApp video. During the question answering, I won't give much time to answer. You should give immediately, and it will be counted also. It is a valid record. It will be considered as a unit test of this unit with this module. So try to be serious. So now compared to the previous, we are going to study little difficult portions. That is the control system module 3. In that time domain analysis we are going to do. Now the time response. So here, that what is the definition of the time response? The time response of a system is the output of closed loop system as a function of time. So time response of the control system is usually divided by two parts: the transient response and the steady state response. Time response of the system is the output of closed loop system as a function of time. Usually C of t denotes the time response of the continuous data system. C of t is equal to CRT plus CSST, where CRT not CRT, C suffix T inside the bracket T denotes the transient response, and CSST denotes the steady state response. In control system, transient response is defined as the part of the time response that goes to zero at the time becomes very large. In control system, the transient response is defined as that part of the time response that goes to zero as time becomes very large. Now, thus C suffix T has the property that indicates that limit t tending to infinity ctt is equal to 0. So just wait for 1 or 2 seconds. Yes. Now, what is transient response? Transient response is called the dynamic response of the system. The state response is simply that part of the total response that remains after the transient has died out. Transient response also called dynamic response of the system. Then what is steady state? Steady state response is simply that part of the total response that remains after the transient has died out. After transient died out, what is the response remains that known as transient response? Now we will see different standard test signals. So we'll see some of the standard test signal. So the first one is step signals. So these are the standard test signals. The step is a signal whose value changes from one level to another level A in 0 time. One level, that is usually 0, to another level, that is A in 0 time. The mathematical representation of the step function is R of t is equal to A into U of t. R of t is equal to A into U of t, where U of t is equal to 1 for t greater than or equal to 0 and it equal to 0 for t less than or equal to 0. Is called the unit step function. U of t is known as unit step functions. Now when you are taking the Laplace transform, this would become R of s is equal to A by s. U of t is represented by A 1 by s. Now second one is ramp signal. The ramp is a signal which starts at a value of 0 and increases linearly with the time like this. This will be the step. Step means before 0 it is 0, at 0 it becomes A, like that. So ramp signal is nothing but the signal which starts at a value of 0 and increases linearly with the time. So this is ramp signal. Now how we can mathematically represent this? R of t is equal to A of t for t greater than 0 and equal to 0 for t less than 0. So in the Laplace transform form, R of s, when you are taking the Laplace transform, R of s is equal to A by s square. So you should understand A of t means 1, A of t, that means A by s square. So this is the ramp signal. Third signal, we are going to study the parabolic signal. The parabolic function represents a signal that is one order faster than the ramp functions. That is one order faster than the ramp functions. The mathematical representation of the signal is R of t is equal to at square by 2 for t greater than 0 and equal to 0 for t less than 0. In the Laplace transform form, you will get it as R of s is equal to A by s raised to 3. So that is represented This is the parabolic signal. Okay, this is parabolic signal. Now, impulse signal. What is an impulse signal? A unit impulse is defined as a signal which has a zero value everywhere except at t is equal to 0, where its magnitude is infinite. A unit impulse is defined as a signal which has zero value everywhere except at t is equal to 0, where its value magnitude is infinite. It is generally called delta function and has the following property. Delta t is equal to 0 for t not equal to 0, and delta t is equal to 0 for t is not equal to 0, and integration of delta t for minus epsilon to epsilon delta t into dt is equal to 1, where delta epsilon tends to 0. So when you are taking the xi and eta, so in the Laplace transform, delta s is equal to 1. Since the perfect impulse cannot be achieved, since a perfect impulse cannot be achieved in practice, it is usually approximated by a pulse of signal with but unit area as shown in figure 41D. So the Laplace transform del of s is equal to 1, and integration minus eta to plus eta delta t dt is equal to 1. It is usually approximated by a pulse of small width but unity area as shown in figure 41D. So you cannot show at a 0 an infinite representation. So it is usually represented by a representation like this, impulse signal. It is having unit area. A into 1 by A, if you are multiplying, you are getting 1. Okay, so it is represented like that, like this. And another important thing is impulse signal is a derivative of a step signal. So, okay, it is a derivative of the step signal. These are things you already aware that. So, the impulse response of a system with a transfer function C of s by R of s is equal to G of s is given by C of s is equal to G of s into R of s, and R of s is, that is 1, so it is become G of s. So C of t is equal to Laplace inverse of G of s, that is G of t. Thus, from this you can understand that the impulse response of a system indicated by G of t is the inverse Laplace transform of its transfer function. Okay, G of s is the transfer function. So we can see that from this example, you can see that C of s is equal to G of s. That's impulse response of a system indicated by G of t. G of t is the inverse Laplace transform of its transfer functions. This is sometimes referred to as weighing function of the system. The weighing function of the system can be used to find the system response to any input R of t by means of convolution integral. Thus, C of t is nothing but integration from 0 to t G of t minus tau R of tau d tau. So here, this is very important thing. The The weighing function of a system can be used to find system response to any input r of t by means of convolution integral, that is c of t is integration from 0 to t g of t minus t r of t into dt. Now next we will see that the time response of the first order time response of the first we will see the time response of first order system. Consider a first order unity feedback system and as shown in figure. It's a first order unity feedback. There is no feedback amplification, it is having unity feedback shown in figure. Physically the system may be represented physically and practically it is represented by RC circuit or thermal system, etc. A simplified block diagram is shown in figure 4.2b. This is a simplified block diagram. Okay, simplified block diagram. The input output relationship transfer function is given by C of s divided by R of s is equal to 1 by T of s plus 1. 1 minute. So here so we are getting this C of s divided by R of s. Now we are getting C of s divided by R of s. C of s divided by, using the same functions, you are getting a feedback like this. Here h is equal to 1. So when h is equal to 1, you are getting it as C of s divided by R of s. C of s divided by R of s is equal to G is here in this circuit. G is 1 by T of s divided by, the feedback sign is minus, you can see the feedback sign is minus, so it becomes 1 by Ts divided by 1 plus G is 1 by Ts, H is equal to 1. So this is equal to, as you can see that it is equal to 1 by Ts divided by Ts into Ts plus 1. So this is equal to Ts is cancelled, it will become 1 by 1 plus Ts. So that is why you are getting here C of s by R of s is equal to 1 divided by Ts plus 1. Now, so here you are getting R of s, C of s, it is simplified as one simple block with 1 divided by Ts plus 1. Now, first order system we come across, if you are applying a unit step to the input of a first order system, what is its response? Okay, so here if you are a unit step for a first system, for a unit step input, R of s is equal to 1 by s. So the output response of the system is given by C of s is equal to, so you know that here C of s divided by R of s is equal to 1 by 1 plus T of s. Then C of s is equal to 1 divided by 1 plus T of s into R of s. Okay. So here input signal is 1 by T of s. So C of s is equal to, as per R of s is 1 by s into 1 divided by T of s plus 1. Now this signal, this expression, if you are rearranging you or mathematically manipulating, it can be written as C of s is equal to 1 by s minus T by T of Ts plus 1. Now if you are taking the common term and if you are putting it, you will get the same equation, because denominator will become s into Ts plus 1, numerator become Ts plus 1 minus, here it becomes Ts. Ts will comes, Ts will cancel, so it will become the same expressions. Okay, that is why this expression is modified into this form. Okay, so this can be again written as 1 by s minus 1 divided by s plus 1 by t. Now, when you are taking the inverse Laplace transform of equation 4.2, what you will get? We are getting it as C of t, 1 by s become 1, and this is a form of e to the power of minus t by, e to the power of minus t by t for t greater than or equal to 0. Now, this states that the output rises exponentially from 0 value to a final value of unity. Final value of unity. One important characteristics of such exponential response curve COT shown in figure 4.3. So this is the important characteristics. C of t is equal to 1 minus e to the power of t by t. This important characteristics. The slope, when you are observing it, it is 1 by t. Okay, the slope is 1 by t, and you can see that how the curve it is. This is a unit step response of a first order system. Yes, so they are representing different points A, B, C, where at the starting the slope is 1 by t, and at A what is the slope, at B what is the slope, and at C what is the slope. That is all represented by the lines. Yes, now the characteristics of exponential curve C of t shown in figure 4.3 is that at t is equal to t, the value of C of t is C of t is 0.632, or the response C of t is reached 63.2% of its initial total change. This may easily seen by substituting t by t is equal to capital T in equation 4.3. That means this c of t is equal to 1 minus e to the power of minus t by t, where small t, if you are substituting capital T, then we become c of t is equal to 1 minus e to the power of minus 1, that is equal to 0.632. So you can see 0.632 at t is equal to t. We are getting the magnitude as 0.632. At 2t, what is the value that you are getting B? At 3t, 95 percentage. At 4t, 98 percentage. 5t, you are getting 99 percentage, like that. So if you are substituting in the previous example, you can see the how the this exponential increase, how it is happening. Yes. Now the initial slope of the curve at t is equal to 0 is given by dc by dt at t is equal to 0 is 1 by t e to the power of minus t by capital T at t is equal to 0, that is equal to 1 by t. The slope is, initial slope is 1 by t. Slope is 1 by t, initial at t is equal to 0. And each time the slope changes. Okay. The slope changes. Now, where t is known as time constant of the system, the output would reach the final value at t is equal to capital T. The output would reach the final value at t is equal to capital T if it is maintained its initial speed response. The slope of the response curve decreases monotonically from 1 by t at t is equal to 0 to 0 at t is equal to infinity. The slope, initially it was 1 by t, then after that the slope decreases and it will become, the slope becomes 0 when t become infinity. So the output would reach the final value of t if it maintains its initial speed of response. Now the error response of the system is given by E of t is equal to R of t minus E of t, that is equal to e to the power of minus t by capital T. So here error signal is obtained. So you know that, yeah, you are having C of t is there, then your input R of s or R of t is there. Now in order to find the error, what you need to do is, error signal can be obtained by R of t minus C of t, that is input signal minus output signal, then you are getting the error signal, that is equal to 1 minus e to the power of 1 minus e to the power of t by capital T, that is equal to e to the power of minus t by capital T. So you're getting that. So the steady state error is given by ESS is equal to limit t tending to 0, E of t that is equal to 0. The steady state error is given. Now, the effect of time constant, you can see that effect of time constant. Here, this is t is equal to t1, t is equal to t2, which is less than t1. This is having a time constant t1. This is having a time constant t2. T2 is less than t1. So you can see the time response, how this is very fast and it will take some more time to reach its final value. So now, here the first order system tracks the unit step input with the steady state error for t greater than or equal to 4 of t. This response remains within 2% of its final value. So this means first order system tracks the unit step input with the zero steady state error we calculate for t with greater than or equal to 40. The response remains within 2% of its final value. Now, when you are coming to all of you, this is not easy to explain also, so be careful and you need to open your text already I had given. So the output response of the next you will see unit ramp response of the first order system. The output response of the first order system for unit ramp input, where R of s is equal to 1 by s square is given by C of s is equal to 1 by s square into 1 by ts plus 1. C of s is nothing but R of s into G of s. Yeah, C of s is equal to R of s into G of s. So you are getting it as 1 by s square into 1 by ts plus 1. Now this expression, the similar way we are rearranging in such a way that the complete answer of this equal to this. So we are getting it as C of s is equal to 1 by s square minus t by s plus t square by ts plus 1. When you are taking the common term and if you are substituting on, you are getting like this only. So here common term is s square into ts plus 1. S square is ts plus 1. Yeah, s square is ts plus 1. S is s into ts plus 1. Like that, if you are arranging it, you are getting the same value. So this, if you are writing 1 by s square t by s, this we are arranging it as t divided by, dividing the numerator and denominator by t, you are getting t divided by s plus 1 by t. Now taking the inverse Laplace transform on equation 4.5, we get C of t is equal to t minus t plus t into e to the power of minus t by tau, or so when you are taking the Laplace transform, you are getting in as t, or this is equal to t minus t into e to the power of t into 1 minus e to the power of t minus t for t greater than or equal to 0. Now the error signal is E of t is R of t minus C of t. When you are doing like that, you are getting it as t into 1 minus e to the power of minus t by capital T, and the steady state error is given by ESS, that is limit t tending to infinity of t, that become capital T. Thus the first order system under consideration will track the unit ramp input with a steady state error t, which is equal to the time constant of the system. So the same method we are using for the each test signal. First you applied a first we applied a unit step input. Then here we are finding the response with a unit ramp signal. Now the smaller the time constant, the smaller the steady state error in the following ramp input. Reduce the time constant, therefore not only improves the speed response but also reduces its steady state error. So here you can see that the C of t is this, R of t is input and output. The steady state error you can see here is t. The steady state error to ramp input can also obtained by applying the final value theorem. E of s is limit t tending to infinity E of t, that is equal to limit s tending to 0 s into es. This is the final value theorem. So limit s tending to 0 s into es means rs minus cs. Limit of s tending to infinity s, rs is 1 by s square, cs is 1 by s square, ts minus 1. If you are doing like that also, you are getting the steady state error as t by using final value theorem.